Hi, my name is Julie Robinson, and I'm a member of the Advanced Functional Membranes REU program at Clemson University. My partner is Ebony Hobley, my mentors are Heather Chenette and Milagro Mariquin, and my advisors are Scott Houston. Today I will talk about the effective surface area on the protein binding capacity of membrane-based cation exchange adsorbers. So in general, this technology is used to separate proteins from undesired biologics for use in pharmaceuticals. My project is motivated by the need for the more efficient downstream processing of proteins due to an increased demand for protein therapeutics. Within downstream processing, the protein capture step remains one of the slowest and most costly. The current industrial method is to use resin-based chromatography. However, these resin bead columns have a low mass throughput and high pressure drop. Thus, there exists a need for a high throughput, low pressure drop technology that can accommodate larger batch sizes in upcoming years. So the goal of my project is to surface modify membranes to create cation exchange adsorbers that exhibit both lower pressure drops and higher mass throughput. Specifically, I investigated the effect of membrane surface area or pore size on protein binding capacity, in addition to comparing the column performance at several different flow rates. Membranes were modified by grafting an FCMAK polymer chains from the surface via ATRP. Regenerated cellulose membranes were chosen as a substrate because they have abundant hydroxyl groups that can be converted to give the membrane functionality. And this is the first step. The surface is activated by converting the hydroxyl groups to bromide using a 2-BIB initiator. The monomer SPMAK was chosen because the sulfate groups are negatively charged, which allows them to react with a positively charged protein. DMSO was used as a solvent because it solubilizes the monomer cap, ligand, and catalyst at ambient temperatures. Additionally, its aprotic nature prevents the solvent from reacting with the catalyst. So here's a little bit how ATRP works. Radicals are generated through a redox reaction, and the polymer chains are grown by the addition of the radicals to each monomer. The reaction lasted 1 hour, and we chose this time because we had a target dry layer thickness of 10 nanometers. Binding capacity measurements were then performed on modified membranes using the active purifier, pictured here. Ion exchange chromatography is a 4-step process in which I'll now explain. The first step is to equilibrate the membrane column with binding buffer. We chose a 50 millimolar tris solution because it has a pH of 8. A pH is important because the lysozyme protein solution used for the binding capacity measurement is positively charged at 8, thus allowing it to react with a negatively charged SPMAK polyelectrolyte chain. The equilibration step is shown by the initial flat baseline on the chromatogram. Next, a sample of 3 mg per milliliter lysozyme solution is injected, and this is indicated by the sharp increase in absorbance. The elution buffer is then run, and for elution, we added 1 molar potassium chloride to the 50 millimolar tris binding buffer. The increase in ionic strength caused the protein to come off the column, which is shown by the peak in absorbance around the 15 milliliter mark. Notice that the modified membranes exhibit this peak, while the chromatogram of the unmodified do not, and this shows that we successfully modified the membranes and protein was bound to the column. At the end of each run, a 0.3 molar potassium hydroxide solution was used to regenerate the line and to remove any residual protein. So presently, the dynamic binding capacity of the 0.2 micrometer membranes was tested at 3 different flow rates, and these flow rates span the range over which the membranes show no adverse response to the subjective pressure. The chart on screen lists the dynamic binding capacity at each flow rate. As you can see, the dynamic binding capacity seems to increase as the flow rate increases, and this occurred contrary to our prediction that the flow rate has no effect on binding capacity. We are not sure why this trend occurs and are currently in the process of investigating this trend further. Dynamic binding capacities are approximated using the expression below. C0 is the initial concentration, which was found by comparing the maximum absorbance as it appears on the plateau on the chromatogram with a calibration curve. The dead volume and breakthrough volumes for the unmodified and modified membranes respectively were found at 10% of the maximum absorbance. The column volume was calculated using the known thickness and surface area of the membrane. Also listed in the table are the percent recoveries, which appear to decrease as the flow rate increases. Once again, we do not yet fully understand this trend and are investigating further. Membrane chromatography offers lower pressure drop and higher throughput than the commercial resin bead column method. The pictures below show that conventional resin beads offer binding sites only on the surface, while grafting polymer chains from the membrane surface creates a 3D scaffold which results in more protein binding sites, hence the higher throughput and lower pressure drop. Now a few notes about our ATRP reaction. The addition of the monomer cap is a unique idea that stabilizes the acidic monomer in an aprotic solution as shown in the diagram. Ascorbic acid was also added in a 1:1 molar ratio with a copper-1 catalyst. This is because copper is easily oxidized, and ascorbic acid is a strong reducing agent capable of reversing copper's oxidation. As previously stated, a dry layer thickness of 10 nanometers was targeted, and this is due to the fact that polymer chains expand in solution and a thickness was needed that would not block the smallest pore when wetted. However, lithography measurements of silicon wafers revealed an actual thickness of only 5 nanometers. As polymer chain length is directly proportional to dynamic binding capacity, this certainly played a role in the low dynamic binding capacities that were observed. So in conclusion, the data presented show how ATRP can be used to create cation exchange adsorbers, and it also demonstrates the relationship between surface area and dynamic binding capacity. In the future, I plan to investigate the effect of polymer chain grafting density on protein binding capacity, in addition to determining the optimal polymerization time or chain length necessary to maximize the binding capacity.
Thank you, Julie. Before we switch over to Evan, we have a couple of questions that have come in. And again, if you have any questions, you can go to the green tab at the top of your screen and enter those to the chat window. The first one is for Julie. Is there an alternate way to calculate the dynamic capacity that is not based on an approximate equation?
Yes. The approximations are for the area under the curve, and there is an integral method, but we are still in the process of computing those.
Okay, and another question we had was, what conditions could you change in the ATRP reaction to vary the polymer chain thickness?
The polymer chain thickness is dependent upon the polymerization time. And so by lengthening the time, that will produce a longer chain.
Excellent. And if you have any other questions for Julie, please type those in. I'll come back at the end. For now, we're going to proceed with handing the presentation over to Evan.
Okay, we talked about the main focus of the overall project. We are looking to surface modify membranes to create cation exchange absorbers with high protein binding capacity and high throughput. The focus of this presentation from here on out is to examine how pore size, flux, and polymer loading affect the performance of the membrane. So to begin, I'm going to talk about the degree of grafting, and here's a schematic. On the left, you can see non-uniform distribution of initiator molecules, and the initiator is kind of clustered, so the localized densities have the potential for pore constriction. And on the right, you can see the desired uniform distribution of initiator molecules. And the space molecules, we use a non-ATRP active molecule. And in this case, we use 1-bromocarbonyl 1-methylethyl acetate, which is 1-DCMA. And then our initiator is 2-bromo-isobutyl bromide. So the initiator graphene density was varied by altering the concentration ratio of 2 BIB to 1 BCMA in solution. So for performance testing of the flux, binding capacity, percent recovery, and concentration measurements, direct flow filtration and active purifier machine was used. And here is data from using an active purifier machine, and it shows the pressure responses for increasing and decreasing flow for 0.2 micrometer, 0.45 micrometer, and 1 micrometer pore size for unmodified membrane. And in this graph, see that increasing flow increases the flux, but also increasing the flow increases the pressure, not as dramatically as you would expect. So increasing the flow doesn't have a big effect on pressure. And then on the left is data from using tris buffer and using GI water as the flow material for flux measurements. And you can see that the data is right on top of each other. So there's no difference in using buffer and from using distilled water for flux measurements. And you can also see that the flow material is not physically affecting the membrane. On the right is data for pressure and flux measurements using 100% activated, 40% activated, and unmodified membranes. And you can see that all the points are on top of each other, so that you can see that the activation of the membranes is not constricting the flow through the membrane. And again, here are more data points similar to figure 6, and therefore 0.5 micrometer and 1 micrometer membranes, and therefore 100% activated and unmodified membranes, and you can see the flux is not changing with activation. So to rediscuss, we could see that the pressure measurements indicate that increasing flow is relatively small for increasing pressure drop, but increasing pressure increases the flux with increasing pore size. And then distilled water and buffer solution did not physically affect the flow through the membrane. So in conclusion, we can say that the activation process does not constrict the pores. And we can also say that from this data, we can use this to create a membrane adsorber that has high throughput. Then in the future, we think it'd be beneficial to study the effects of flow rate and ionic strength on binding capacity performance. Also, it'd be interesting to understand the effects of polymer chain length on binding capacity and pressure drop for the pore sizes tested. And also, we would like to use the results we got here on inverted collodial crystals, which are more spherical and uniform membranes. And here are my references for the graphs I used in the presentation.
Thank you very much, Ebony. We have several questions coming in. Again, if you have a question for either of our presenters today, at the top of your screen is a green tab that opens the chat window. you can send those in. The first question is for Ebony. It seems like more chains are desired for higher binding capacities, but could long chains cause a higher pressure drop? And which pore size would you expect to be most affected by that?
The pore size we would expect to be most affected by lengthening chains are 0.2 micrometer, because their pore sizes are so small that it'd be easier for clustering to happen. But we have yet to test the effect of length on the pore sizes, and that's what I'll be testing next week.
Excellent. You have your time cut off for you. Second question is, have you examined how polymerization impacts forms?
And that will be what I'll be looking at next week after I'm able to take these same pore sizes and do ATRP polymerization.
Okay, and this is a general question for either of you from Chris. Can you use surface data potential measurement to characterize protein binding? And I'll let the two of you have a fun word to decide who wants to answer that. The question was again, can you use surface data potential measurement to characterize protein binding? Anyone think it's looks like we don't have an answer for that one. And one other question here, maybe it's just something you can think about, and I'll let you get in touch with Chris after this. What benefits does ATRP have as a polymerization method over other chain growth methods? I think that might have been for Julie. It was early on. So we're wondering what benefits ATRP has over other chain growth methods. I'm not sure if you're familiar with any other methods.
Well, one of the reasons we use ATRP is because it allows better control over not only the thickness of the polymer chains, but also the density, as Ebony was talking about.
I guess I could add to that, and for ion exchange membranes, it's controlled by a convective flow process, so it's less dependent on the flow rate, and current methods are more controlled by diffusion, so it takes time for the protein to reach the binding site, and so in the way we're doing it, it should happen faster.
Okay, excellent. That's all the questions we have time for.